Alright, so this is section 2.8, derivative as a function. We're going to start by recalling something that you've seen on the previous sections. So you're going to see here, this is a derivative of a function f at a fixed number a. So we're going to basically use this to find the derivative at a specific or at a given x value, okay? Now the next one is pretty much the same thing. You're still finding the derivative of a function, but this is just the function in general, like in general terms, so in terms of x, okay? Now we are going, when we're talking about the derivative of a function, there's different ways that you're going to see either on the textbook or in other places. So we're going to have f prime of x is the same thing as y prime, is the same thing as the derivative of y with respect to x, derivative of f with respect to x, and so on. So all this means the derivative of a function. The most common ones that I see are probably like the first four. So those are basically the ones that you're going to see from me. This one, some textbooks like to use it, but they mean exactly the same thing. So derivative of f of x, the derivative with respect to x of f of x. So they all mean the exact same thing. They all mean the derivative of a function in terms of x. Now later on in this class, you're going to learn that sometimes we can take the derivative with respect to y or to another variable, okay? Alright, so let's move on to example 1. Derivative of a function by a graph. So here, the first graph is f of x. And the second graph, the graph that you see right below, let me make it smaller so that way you can see both at the same time. This one is f prime of x. So this is a function. If you take the derivative of the function and you graph it, you will have this right here. Now let's look at this. What we need to know here is that the slope at a given point on your original function is going to be equal to the value, to the y value on f prime of x. So for example, let's look at point A. So right here. The slope right here is flat, is a zero slope. Now if we go on to our f prime of x graph, our derivative, I'm going to try to draw an arrow here. Look at a prime right here. What is the y value at this point? Is 0, right? So the slope of the graph is the y value of your derivative graph, okay? So same thing happens here. If you look at b, the slope right here at b is 0. That's exactly your y value here. So notice c, the slope is 0. That's your y value. They're basically your x-intercepts, okay? Now let's look at point P. Point P, the slope at this point is 3 over 2, which is equal to 1.5. Now I want you to look at the y value of point P. It's exactly the same thing. So that's how you can see the relationship between the original graph and the graph of the derivative of the function, okay? So on the next page, we're going to basically practice what we have here. You're going to have to mix and match. So the first four, it says match the graph of each function a through d with the graph of the derivative. So the first four are your original functions, f of x, and then 1 through 4 are the derivatives, okay? So you have to label which one goes with which, okay? So maybe you say, oh, I think a goes with number 2, or a goes with whatever. So I'm going to give you guys some time to look at this and you can check your answers, okay? All right, so make sure you have an answer for this. So I'm going to try to make it smaller so we can see all the graphs at the same time. Okay, so what I need to focus here, or what I would like for you to focus, is on some points here where the slope is 0, just like on the previous one, because I know those are going to be my x-intercepts basically on my derivative. So that's kind of how I can do this by process of elimination. So remember, these 4 graphs are your f of x, your original ones, and this 4 are the derivatives. You have to match them. All right, so if you look at this one, I'm supposed to have an x-intercept here and here. So I kind of see this one kind of crosses there, and this one kind of crosses there. So maybe I don't want to do this one first. How about C? Let's start with C. That one looks easier. I see there's a 0 slope right here. So that means at 0, it has to cross through 0. Okay, we have this one and this one. But this one crosses here and here as well. So this one should only cross at 0, 0. So the only one that crosses at 0, 0 will be I. So I goes with C. So the graph of C, the derivative, if we graph it, is going to look just like I. So I don't know if you guys want to put like the letter next to it, so that way I don't have a bunch of lines. Or you can even put the letter on the derivative. Okay. All right, so we have that one out. Now, this one should only cross twice the x-axis, not 3 times. This one crosses 3 times. So that means number 2 will have to go with with letter A, because it should only cross here and here, and that's exactly what happened there. So this one goes with A. All right, now let's look at this one. It looks like I have a 0 slope right here, and here, and here. So that means it crosses the x-axis at those 3 places, here, here, and here. So that means number 3 has to go with D. Has to go with D. There you go. Now by process of elimination, B has to go with number 4. And we're going to talk about this one right now, because this one is special. Okay. All right. Now let's move on to example number 3, which is on the next page. And notice I already have something here, because for number 3, we need to find the derivative of a function by a formula. So we have to use the formula to find the derivative. I know a lot of you guys probably already know how to find the derivative without using the formula, but that's going to come until we get to chapter 3, okay? So for now, you get to use the formula. Now we're going to use this one because they're asking you to do it in general terms, in terms of x, so that's why we're using this, okay? So I'm going to have you guys give it a try. Pause the video, plug in everything, and do the baby math so you're going to simplify it, okay? So pause the video, and then you can check your answer with me. Okay, so you can see the first part where I plug everything in, and then you can do the baby math and check your final answer. I'll let you do this. All right, so then here comes the fun part where you have to simplify everything. I'm gonna write it myself, and then you guys can check your answers, but you please try it yourself first, okay? All right, so here we have this. I distribute this to the third power, and I wrote everything everything out, I distribute the negative signs inside the parentheses, and then I did some simplification. Once you do that, notice you still have an h in every term, so you can factor that one out and then divide it with the h on the denominator, okay? When you're doing this, notice that you're always going to end up canceling this h on the denominator or dividing it out, because we don't want, remember, your limit that you're taking is going to 0. So you don't want 0 in the denominator. So normally that's what's going to happen. Now I'm left with this, but since I'm taking the limit and this goes to 0, this whole thing is going to go to 0. This whole thing is going to go to 0. So you're left with 3x squared minus 1, and that's your answer, okay? If you have any questions on any part of this, please make a note and I can answer them during class. All right, on the next one, we're going to do pretty much the same thing. Now, when you do this, remember we're going to be using the exact same formula. I'll help you write it. Don't forget to write the limit on every single one, okay? Because you are taking the limit. I'm going to do x plus h minus f of x all over h. Now notice here we have square roots on the numerator. So what you want to do is rationalize the numerator. And we've done this before. So this is another fun baby math, okay? So I'll let you guys work on this, simplify it, and then check your answer with me, okay? Remember, when you rationalize the numerator, you want to multiply it like this, this like this, this like this, okay? Because the middle terms are going to cancel out. So work on that, and then you can check your answer with me. All right, so after you simplify, we end up with this here. Remember, h goes to 0 because you're taking the limit as h approaches 0. So we end up with 1 over 2 square root of x. Now, I forgot that we're also finding the domain of f and f prime of x, okay? So this is the last part we're doing. So here we have to find the domain of f of x, which is the square root of x. Now in this case, x has to be greater than or equal to 0. So if you write it with interval notation, that will be bracket 0 to positive infinity, okay? Now if we look at the derivative of this function, we have to pay attention to the denominator here. So x has to be greater than or equal to 0, because the denominator, 2 square root of x, cannot be equal to 0, correct? Because we cannot have 0 in the denominator. So because of this, we know that x has to be greater than 0. And because x has to be greater than 0, we can rewrite it as 0 to positive infinity, where 0 is not going to be included, okay? Alrighty, there's one definition on this page. And it says, function f is differentiable at a if f prime of a exists. If it is differentiable on an open interval a to b, or a to infinity, or negative infinity to a, or negative infinity to positive infinity, if it is differentiable at every number in the interval, okay? So it is differentiable in the open interval if it is differentiable in every single number that includes the interval, okay? Theorem, if f is differentiable at a, then f is continuous at a. But the converse does not work. So remember, this is a if and then. So if this, then this happens, okay? The converse of this will be the other way around. So if and then is like this. If this, then this happens, right? The converse will be the other way around. So this is saying that if it's continuous, not necessarily is going to be differentiable at A. So it doesn't always work, okay? That's what it means. All right, I'm going to jump into the last page because I want to work with the page number 4 in class, okay? Okay, so example number, I believe is example number 4 on page 4 is what we're going to do in class together, and basically shows what this page is saying, okay? So it says, how can a function fail to be differentiable? So there's 3 things. One, if the graph of the function has a corner, so basically kind of like this, right? It's pointy. Then the graph has no tangent at this point. F is not differentiable here, okay? 2, at any discontinuity, F fails to be differentiable. So here is not continuous at A. Why? Because it jumps. That means it's not differentiable at this point here. And 3, the curve has a vertical tangent line when x is equal to A, that is if f is continuous at A and the limit as x approaches A of the absolute value of the f prime of x is equal to infinity. So here we have a vertical tangent, then that means it's not differentiable, okay? Alrighty then, but we're going to show an example where it's not differentiable on example 4. I want to do that in class. Alright, definition, higher derivatives. So second derivative is denoted with the 2 little lines here, and is the derivative of the derivative. And these are just different notations of how to find the second, or how to define the second derivative, okay? But basically, you cannot take the second derivative if you don't take the first derivative. So in order to take the second one, you have to find the first one first. So, and by the way, we can have the first derivative, the second derivative, the third derivative, and so on. But you have to do it in order, okay? So here, I'm going to take the derivative of this, just like we did on the previous page. Remember, I have to plug in x plus h squared minus f of x. And this is a formula that you should memorize, okay? It's basically the definition of a derivative. All right, so here's where we do the baby math. We distribute everything and we simplify if we can. So notice here the x's are going to go away, and then we can factor an h and cancel it with the denominator, which is what we want here. X plus h, there you go. And notice here, this is going to cancel out. So I'm going to be left with the limit as h approaches 0 of 2x plus h. But we got to remember that since we're taking the limit, h goes to 0. So basically, my answer is going to be just 2x. When you're taking your derivative, your derivative should not have h in it, okay? Why? Because you're taking the limit as h approaches 0, so the h's should go away, okay? Always, always, always. All right, now this is the first derivative of f of x. I need to find the second derivative. Now to find the second derivative, I need to reuse the first one so I can take the next one, okay? So basically, I'm going to do the same thing again, but now my function is this here. So I'm going to take the limit as h approaches 0, and I highly recommend you to pause the video right now and just try it yourself and then check your answer. This one is a little bit easier. So once you take, the more derivatives you take, the easier it gets because the functions get a little bit smaller and smaller. And yes, you do have to put the limit as h approaches 0 every single time. Alright, so let's simplify here. This is 0. I can divide out the h and I'm left with just 2. So the second derivative is going to be 2. And that's it. Alrighty, so we're going to finish example 4 in class together. So thank you for watching this.